Hello and welcome to The Explainer. Today we are going on a fascinating journey. We're going to start with the super complex camera that's literally inside your own head, and we'll end up with the huge, colorful world all around us. So, let's dive right in.
You've probably looked up at the night sky and wondered this exact thing, right? It's one of those classic questions. And I promise, by the end of this explainer, you're going to know the precise physics behind it. We're going to build up to that answer piece by piece.
So here's our game plan for today. We'll start small, really small, with the mechanics of your eye. Then we're going to zoom all the way out to the big picture, the amazing light shows we see in the sky every single day. All right, first up, let's get personal. We're talking about that incredible piece of biological tech you're using to watch this right now, your eyes.
You know, the easiest way to think about your eye is as this amazing self-focusing camera. Light comes in, a lens system focuses it, and boom, an image gets formed on a screen. The really incredible part is that this all happens instantly, without you even thinking about it.
And what's so cool is how all these parts work together, kind of like a team. The cornea, that's your heavy lifter. It does most of the initial light bending. Then you've got the iris and pupil. They act like a camera's aperture, deciding how much light gets in. The lens then does all the delicate fine-tuning. And finally, the retina acts like the film or the digital sensor, capturing the image and sending it off to the brain.
And that brings us to the eye's absolute superpower, the power of accommodation. Now, this is a super important concept, and you see it a lot in exams. It's basically magic performed by these tiny things called ciliary muscles. They squeeze and relax the lens to change its shape, and that's what lets you instantly shift your focus from, say, your phone screen right in front of you to a tree way off in the distance. But even that superpower has its limits. For a normal, healthy eye, this is pretty much the boundary, 25 centimeters. It's called the near point. You can try it right now. Bring something any closer than that, and your ciliary muscles just can't squeeze the lens hard enough to keep it sharp. It's the physical limit of your clear, up-close vision. Of course, just like any camera, sometimes our eyes can have focusing issues. So let's talk about some of the most common glitches in the human eye and the really simple physics behind why they happen.
Okay, so here are the big three you really need to know. First is myopia, which you probably know as nearsightedness. That's when you can see things up close just fine, but stuff far away is blurry. Hypermetropia, or farsightedness, is the exact opposite. And then there's presbyopia, which is that loss of focusing power, that power of accommodation we just talked about, that often happens as we get older.
So what's actually going on here, physically? Well, for myopia, the eyeball is just a little too long, so the image comes into focus before it even reaches the retina. With hypermetropia, the eyeball is a bit too short, so the image tries to focus behind the retina. Either way, the image that lands on the retina itself is blurry.
All right, pop quiz time. Here's a classic exam-style question that uses exactly what we just learned. A student can't see a distant object clearly. Think back to our chart. What's the defect? And if you said myopia, you absolutely nailed it. To the eye, the blackboard is basically at infinity. But this student's far point is much, much closer. The fix? A concave lens, which will adjust the light's focus and get that image right where it needs to be.
So, we've identified the problems. Now let's look at the really elegant physics-based solutions that let millions and millions of us see the world clearly.
It really is all about redirecting light. For myopia, remember, the focus point is falling short. So, a concave lens diverges or spreads out the light rays just enough to push that focal point backward, right onto the retina. For hypermetropia, a convex lens does the opposite. It converges the light, pulling that focus point forward, again, right onto the retina. Simple, but brilliant.
All right, we've pretty much become experts on the eye as a camera and how to fix it. But what about the light itself? To really get the whole picture of vision, we have to zoom out from the eye and look at the incredible physics of the very thing it's designed to see. This is where our world gets all of its color. This amazing effect is called dispersion. You've probably seen it. When white light, like sunlight, passes through something like a glass prism, it splits into a whole spectrum of colors. And you can remember the order with that classic acronym, VIBJOR.
violet, indigo, blue, green, yellow, orange, and red. Pretty cool stuff, first shown by Isaac Newton himself.
So how does that give us a rainbow? Well, it's this awesome three-step dance that happens inside millions of tiny raindrops all at once. Each little drop acts like a tiny prism. First, light enters the drop and disperses into colors. Second, those colors bounce off the back of the raindrop. And third, the light exits the drop, now separated into that beautiful arc of color that we see. Okay, from a single raindrop, let's zoom out one last time to the entire atmosphere, which it turns out is putting on a spectacular light show for us every single day.
And here we are. We're back where we started. That big question. We have all the pieces of the puzzle now, so are you ready for the answer?
The whole answer comes down to one thing: distance. Stars are so incredibly far away that to us, they're just single points. As that one tiny beam of light travels through our shaky, turbulent atmosphere, it gets bent and bounced around, which makes it look like it's flickering. But planets, they're much, much closer. So we see them not as one point, but as an extended source, like a little disk made of many, many points of light. While each individual point might be twinkling, all those twinkles average out, giving us that steady, solid glow.
And get this, that same bending of light in our atmosphere that makes stars twinkle, it pulls off an incredible magic trick on us every single day. Because our atmosphere bends sunlight around the curve of the Earth, we actually see the sun for about 2 minutes before it has physically risen above the horizon. And we keep seeing it for 2 minutes after it is already set. That means our day is literally about 4 minutes longer, all thanks to physics. How wild is that?
Okay, one more big question about the world around us. And no, the answer isn't because it's reflecting the ocean. The real reason has to do with tiny, tiny particles in the air. It all comes down to one word: scattering. See, the little nitrogen and oxygen molecules in our air are just the right size to be really good at scattering short wavelengths of light, which happen to be blue and violet light. So as sunlight comes in, these particles scatter the blue light in all directions, just bouncing it all over the place, which makes the whole sky look blue to us. The longer wavelength, like red light, tend to just pass straight through. That's also why emergency signals are red, because red light is the least scattered, so it travels the farthest through things like fog or smoke. And that brings us to one last really powerful thought. If the blue sky is caused by light scattering off our atmosphere, what happens when you leave that atmosphere behind? Well, for an astronaut in space, there's nothing. No particles to scatter the sunlight. So without any scattering, the sky is just the deep, inky black of space, even when the sun is shining brightly. It's a perfect reminder of the beautiful, invisible physics happening right over our heads. Something to think about the next time you look up.